Okay, here's another example with rigid body kinematics. And this is a pulley problem. So we are doing rigid body kinematics continued because we've been doing a whole bunch of examples with that flavor. Example. So this is a composite pulley problem. What do we mean by that? So we have, this is the pulley, and it's got sort of two radii, and the outer radius is attached to a rope. The inner radius is attached to a different rope, and this rope is being pulled at 3 meters per second, and this rope is being pulled at 4 meters per second, and this whole thing is a single rigid body. Okay, so I'm going to label some points here. Let's call this point B, this point O, and this point A, and this radius, this inner radius is R1, and this outer radius is R2. Okay, so this is the setup of the problem. So what's given? We are given a composite pulley with radii R1 equals 1 meter, R2 equals 2 meters, is a single rigid body. Okay, what do we mean by that? So this thing is the pulley, and even though there are these two radii, it's not like the inner radius rotates relative to the outer radius. This whole thing moves as a single rigid body. In other words, points A, O, and B on the rigid body are all essentially are on the same rigid body, right? So they all move in a manner that the distances between them do not change, etc. Okay, so it's a single rigid body, and it says two, like I just said, two different ropes are attached to the two radii and are pulled up with different velocities. As shown. The most important sort of condition is that the ropes do not slip against the pulley. Okay, so no slip. Okay, and then you're asked to find angular velocity of the pulley. Omega equals omega k of pulley. So that's one. And then the other thing we are asked to find is velocity V naught of point O, which is the center of the pulley. Okay. Okay, so those are the questions. Now, what can we do? The first thing to note is that points A, B, and O are on the pulley, and point A essentially touches this rope. Point B touches this rope. The point on the rope that touches A is moving up with 3 meters per second because this point on the rope is moving at 3 meters per second. And because the rope is inextensible, every point underneath that point is moving at 3 meters per second, including this point. So if you have a point A here on the pulley, that point will also move at 3 meters per second, and that's what we mean by no slip. No slip means the 2 points move with the same velocity so that they do not have any relative velocity. Okay, so what do we mean? All that means is that if we say this is J and this is I, the velocity of point A is basically 3 meters per second upward. The velocity of point B on the pulley is 4 meters per second upward. So let's write those things down. No slip implies VA equals 3J meters per second. VB equals, sorry, I guess that's right. VB is 4 meters per second J. Now, what can we do? We can use the rigid body velocity equation to connect A with O and B with O. Let's do that. So consider A. So we have VA equals 3J, but VA is also equal to V naught plus omega K cross R A with respect to O. So we have 3J equals V naught plus what is RA with respect to O? This is the point A, this is the point O. A is just to the left of O. So let me just draw a picture there. So if you have O here, we have A here. This vector is basically minus R2I. Right, so we have omega K crossed with minus R2I. That's A with respect to O. We can simplify this a bit further. We have plus minus R2 omega. K cross I is J. So we can rearrange this equation as V equals 3 plus R2 omega J. Okay, so that's what we get. Let's call that equation number 1. Now consider B. We can write the same kind of equation. VB equals VO plus omega K crossed with RB with respect to O. VB is 4J. VO is unknown, so we just leave it as it is, plus omega K cross RB with respect to O. So B is here, O is here, so if you have O is a vector to B, this is basically R1I, okay? So that vector is R1I. So let's write that down here. And let's simplify a little bit. We get 4j equals v naught plus r1 omega. K cross I is j again. Then we rearrange to get v naught equals 4 minus r1 omega j. Okay, so let's call that equation 2. Now we have two equations and a couple of unknowns. So first of all, we now know that v naught is only in the j direction, so or vo. This is a point O. Points A and B are moving upward, and we've just realized that the point O is also moving upward because it's got only j components. Okay, this is not something that we assumed, but something that came naturally out of our equations that we have. Okay, so we need to solve for v naught or vo and omega. Let's do that. So equating v naught from 1 and 2, or vo from we have 3 plus r2 omega j equals 4 minus r1 omega j. You can sort of ignore the j's. So we have, bring the r1 omega here. So we have r1 plus r2 omega equals 4 minus 3, or omega equals 1 over r1 plus r2, which we said were 1 and 2 respectively. So that's going to be 1 over 1 plus 2 equals 1 over 3. Okay, so that's 1 over 3 radians per second, or that is omega equals this is an answer. And then now that we found omega, we can use either this equation or this equation to calculate v naught as well. So let's do that. So we're going to have v naught equals 3 plus r2 omega j equals 3 plus r2 happens to be 2, omega happens to be 1 over 3 j, and that's going to be equal to roughly 3.667 meters per second j. Okay, so that's v naught. And that's the other answer. And that's the end. So what did we do? We were told about this pulley, which is a single rigid body. Two ropes are connected to two different radii, and they're going at two different velocities. And because there's no slip, the rope velocity is the same as the points on the pulley that are touching the rope. And then we are using this equation that relates velocities of different points on a rigid body, and essentially using sort of two such equations to solve for all the unknowns. And that's it.